Thank you very much for the introduction, Michal. So hi, everyone. I'm Omar, and I'm going to guide you through the reinforcement learning tutorial I prepared for you. So let's get to it. So as a quick recap, as you saw earlier today, in reinforcement learning, we are interested in learning policies that allow an agent to act optimally in an environment. So we have these two fundamental concepts in reinforcement learning, the one of policy and the one of value function. A policy is a function that's mapping every state to the action that the agent has to take, or to a probability distribution over actions, if the policy is stochastic. And the value function is measuring how much reward we can expect to gain by taking an action A, starting from a state S. And in this tutorial, we're going to focus on methods to approximate the optimal Q function. And also, as you saw earlier today, if you have an optimal Q function Q star, you can obtain one optimal policy by taking the argmax over actions. So if in every state S, you know the value of taking an action, you can take an optimal policy by maximizing over action. So every time, every state, you take the action maximizing the value. So you can obtain a policy, an optimal policy from an optimal Q function. So we can focus on approximating the optimal Q function. So I split this tutorial in 3 parts today. So I know some of you have never seen RL before in your lives, whereas others have done research on it. Maybe some are doing their PhDs or have more experience. So I tried to adapt the tutorial to the wide range of experience we have here. So there are 3 parts. The first part, it starts with very simple environments with finite states and actions. And if you know the dynamics of the environment, so if you know the reward function and the transition probabilities exactly, you can run value iteration, applying the Bellman operator, to obtain the optimal policy, one optimal policy. And if you have an environment that you don't know, so you can only sample from it, only taking actions and observing outcomes, you can use qlearning. So that's the first part. Finite spaces, finite actions, where everything is simple and easy. Then we're going to move to the part 2, where we can have possibly large or continuous state spaces. And there we need function approximation. So we can start from linear function approximation with handcrafted features. So we don't use handcrafted features today anymore, but it's useful to see some trade-offs, to see what happens when you have bad features, just to build some intuition on function approximation. Then the part 3 is about deep qlearning, so DQN, using deep Q networks, where you use a neural network to approximate the Q function. So the features are kind of learned implicitly by your network, trying to approximate the optimal Q function. So here are my suggestions. So if you are a beginner, so if you never coded anything in reinforcement learning before, there is an introduction notebook recapping everything. So not everything, the basics that you need for the tutorial. And then I recommend you following part 1, part 3, and if you have time, go to part 2. If you're intermediate, so if you have coded DQN before in your life, I suggest you start looking at part 2, but optionally, and then go implement DQN. And I also put a challenge in the 3rd notebook. So there you can explore more crazy things. So if you want to try the latest cool algorithms that Michal just presented, you can go to notebook 3 and tackle the challenge. And if you're advanced, if you know DQN, just implement it quickly and go to the challenge to have some fun. And here's how it's going to happen, everything. So you can code freely and explore the notebooks as you want. And don't hesitate to collaborate with your colleagues around you, so it can be helpful. And you can ask us any questions anytime, so me or the TAs who are there. And every 25 minutes, I will solve one notebook with you and guide you towards the next. So right after these slides, I'm going to guide you for the first one. And another thing, if you have a question that is more general, more conceptual, please raise one hand so we can give you a mic and ask for everyone. If you have code problems and need help that's specific to your code, you can raise 2 hands and say, hey, help me, and we go there to help you. OK, so I'm going to get to it when we get to part 3 to give you some tips. So now let me show you. So now so I told you what to do if you're a beginner, intermediate, or advanced. I'm going to follow the path for the beginners because, yeah, that's our focus here. So in the introduction notebook, the first thing you have to check, so we have there is a Colab setup, installing the main libraries you're going to need. And an important part is here, so showing you how to interact with a reinforcement learning environment in Python. We are using the Gymnasium API for that. It's quite standard. So let me zoom a little bit. Sorry. So you can see better. Yeah. So here you have to, so you can check the Gymnasium website to explore some environments. So here I'm using the Lunar Lander environment. So environments, they are defined by a string ID. You can create them like this. And there are two important functions that you have. The reset function, that is putting your environment in an initial state and returning the initial state or observation. So states and observations in this tutorial, they are the same thing. And then, so you can reset the environment to put it in initial state. And when you want to take an action on the environment to observe the outcome, you call the step function. So you call environment.step for any action that you want to take. And when you take the action, you observe the next state, the reward, and a flag. So terminated or truncated, which I'm going to explain now. So for example, if your environment is Lunar Lander, so here we are trying to learn a policy to make our rocket land between the two flags here. A terminal state is reached when your episode is ended. So for example, when your rocket lands, or if you're trying to balance some bar when the bar falls down, or when your robot reaches its goal, you're going to have a flag indicating that. So true if the episode has ended. So you can use that. OK, and then if you need, there are some, I try to summarize some main concepts here and the algorithms that you have to implement. Now let's go to the, oh yeah, all the notebooks are here in the GitHub of the summer school. So I just show you the introduction notebook. And to open it, you can just click on the notebook and then open in Colab. Yeah, here. So for part one, so yeah, I didn't say, but the tutorials, they can seem quite long, but in terms of coding, there are basically 10 lines in total that you have to code to make things work. So the difficult part is knowing exactly what you code. And for that, I put some hints. So here, for the first part, you're going to start with, oh yeah, the environment we're tackling. This first part is a very simple grid word. So here, as I said, we start simple. So the environment is this one. So it's a 2D world. And you have an agent with this magenta diamond shape trying to learn how to reach the green flag at the bottom right. And there is this wall here just to make things a little bit more interesting. So here I'm showing you a random policy. And then you have to implement two things in this tutorial. The first one is the Bellman operator. So as you saw in the lectures, to find the optimal Q function, you can look for the fixed point of this Bellman operator. And for that, you can just iterate. So if you start from a 0 function, apply the Bellman operator very many times, it will converge to the optimal value function. And the challenge here is, of course, you need to compute this sum. When your state space gets larger or continuous, this becomes very complicated. But here's a simple case where you can do it. So you have to implement. So yeah, anytime you have to code something, you're going to find this big comment saying your implementation here. So I'm going to find it in the notebooks. And all you have to do in this part is to write 1 or 2 lines computing the Bellman operator. I just showed you the solution. I hope you didn't get it. Yeah. I was coding myself. Yeah. So just to show you this. So when you get the solution, your agent will reach the green flag. And you're going to see the convergence. All right. And then I'm not going to show you the solution for qlearning, but it's the same. You have the equation here and the line where you have to implement hiding the solution again. Oops. just compute your delta. Oops, again. Yeah, basically it's going to work if you implement correctly, and you see that the convergence is quite long. That's it. So I'll come back in 20, 25 minutes to follow up on this and to guide you to the next notebook so you can start coding. And don't forget, 1 hand for general questions, 2 hands for code. Yeah, and just trying to give you some extra motivation, maybe not so motivating, but in the end, we're going to move towards more interesting environments. So for deep qlearning, there's this pole balancing task, and you'll also be able to handle the lunar lander environment that I showed with DQ and this one.
hates us. This is so простой.
YouTube confused as well.
So if it's not clear for anyone how to interact with the reinforcement learning environments in Python, please raise your hand. Okay. Okay, so that we can advance slowly, I've been showing the solution for a few minutes. I don't know if you noticed, for the first part, for value iteration. So it's here. I'm going to display it in another notebook so I can keep track of the solutions. So if it's not clear for you how this equation translates to this implementation, let me know. No? All right, so let's recap what's happening here in this first part, in the value iteration part. So as I said, the optimal Q function is the fixed point of the priamo operator. In some cases, it's easy to compute this fixed point. And precisely here, it's easy because we have access to the reward function. So this operator relies on the reward function and the transition probabilities. And you see that in this function, we have access to both. So we have the P, we have R, reward function and transitions. So, and it's easy to compute this sum. So everything is discrete, so you can store rewards, transitions, and Q functions in NumPy arrays. So no memory issue, no computational issue, so it's easy. It converges quite fast. So if we look at the error, as we increase the number of iterations, it goes down very quickly because the environment is small, it's very easy. And by following the greedy policy with respect to the value function, and by greedy, I mean the one that's taking the action maximizing Q in every state, we get this policy. So the agent learns how to move to this green flag and avoiding the wall. But there are two important things here. So in reality, we don't know the reward function exactly. We don't know P. If you take an Atari game, you don't have a description, you don't have a table with the reward function. You don't have a table with the transition probabilities. We don't know this for the word. So if you're learning how to interact with the word, if you're learning how to recommend movies to someone on Netflix or songs on Spotify, you don't have access to these true transitions or these true rewards. So you cannot compute this operator exactly. Another case is even if you know the dynamics of environments. So if you're learning how to control a robot and you modeled the dynamics and the rewards very precisely with equations coming from physics, the state space can be very large, so it can be hard to compute exactly this Belmont operator. So that's when we start moving to reinforcement learning. So this is more dynamic programming, actually. So not really reinforcement learning, I'd say. Depends on your definition. But when we start moving towards reinforcement learning when we don't know these quantities. So we need sampling from the environment to estimate this Belmont operator, to estimate the optimal Q function, or to estimate directly the optimal policy. So that's a step that we are taking. In the next part, we are implementing qlearning, so tabular qlearning, and by tabular I mean that we can store everything in tables, in NumPy arrays. So here, we don't need to know the reward function exactly, we don't need to know the transitions. All we need is to be able to sample from the environment. So if you remember what I was saying about the Gymnasium API, all we need is some object on which we can call the step method and with an action and observe the next state and the reward. So that's when we move to qlearning. So I'm going to implement this with you now so we can move towards more interesting parts since time is passing fast. So in qlearning, so if you look at the code, you don't require any more R, the NumPy array with rewards, or P, the NumPy array with the transitions. We are only taking the environment as input and some parameters. So the discount factor that controls how we balance between short-term and long-term rewards. For example, so if gamma is very close to 1, we are interested in a very large time horizon for the rewards. If gamma is small.
Excuse me, could
Yes?
you please zoom in a little bit more?
Of course, thanks. Yeah, should be good. Okay, so as I was saying, here we don't need to know the rewards or the transitions exactly. All we need is this environment from which we can sample. So if you look, I'm using this because I'm lazy. I'm taking the number of states and actions, but I could also have taken, if following the API, I think observation space.n. So this would also work. So I could put action space here. So this would also work. So yeah, we still need some information about the domain. So what is our possible states or possible actions? But besides that, all we use from our environment is the reset function. So we need to, when we reach the end of an episode, the end of a trajectory, we need to be able to come back to an initial state. And we are also using the step function to sample from the environment. And once we sample from the environment, what we're doing here is we start from a Q function that is 0. Then we want to increment it towards the optimal Q function. So very similar to some sort of gradient descent. So if you look at this formula, we are trying some sort of stochastic approximation of the Belmont operator, right? So if you look here, when is your delta 0? So delta is a measure of error. So you can look at as the gradient or some step that you need to take in the direction of the optimal Q function. So if you look at when the delta is 0, is when Q, the Q function in your state and action, is equal to reward plus gamma, the maximum here. And if you look at the Belmont operator, you can see some similarity between these two things, right? So here, let me show you. So have the delta here. And if you look at the Belmont operator, it also has something involving reward plus gamma times some maximum, right? So instead of summing over all possible states, we are only using the sample next state. So instead of having this sum, we only have S prime equals to the next state that we sampled. So that's the intuition behind this qlearning update. We are incrementing our Q function to trying to on average, reduce the difference between Q and the Bellman operator applied to Q. And there are other parameters there. There's the learning rate. So if I show you the update, so the update is very similar to gradient descent, as I was saying. So you have something that you want to improve, and you add some learning rate times delta. And delta, just as I described. And yeah, then you have the learning rate parameter to control. And another thing that is very important, so how are we going to interact with the environment, right? So, okay, yeah, we have this update rule, but how are we sampling actions to collect data? So as you notice, a fundamental difference between reinforcement learning and supervised learning, for example, is that, well, besides all the setup, is that in reinforcement learning, the agent needs to collect its own data to learn. So it's very important to define a strategy for collecting data. And here we are using an Epsilon greedy strategy. So we can think of the extreme case where we are just sampling random actions. But if you look at our grid world here, to our environment, if you sample everything just randomly, it can take a long time. Sorry, I'm going to decrease the zoom a little bit just so we can see the environment. So if you just take random actions, so if we start here on the bottom left, and you want to go to the bottom right, and you just take random actions, if the environment is very large, it can take a huge amount of time just to reach that flag by chance, right? So, and before you reach the flag, you have no reward, so you have no signal to learn from. So it's complicated. One thing that you can try to do is some Epsilon greedy update, where with some certain probability epsilon, so you take a random action, and otherwise you try to follow the best action follow according to your current estimate of the Q function. So you try to mix random exploration with some greedy exploration. That's what it's called, why it's called epsilon greedy. Epsilon for random and greedy for greedy with respect to Q here. So yeah, when you implement it, so if you haven't had the time to finish it, you can start debugging with the easy environment. So it's just a smaller version of the grid world. You can set it to true. But basically, you're going to have some sort of convergence, like error like this. So in the beginning, you see that it's very flat. And this is because the exploration is random. So in the beginning, the agent starts here. So let me go to the beginning. Sorry, yeah. So the agent starts here, and it starts exploring randomly. And before the agent reaches for the first time the flag here, all the rewards were 0. And what happens when the rewards are 0? There's no update. So if you start with Q equals to 0, reward is 0, your delta is 0, so you have no signal to update from, right? So until you start getting some reward, you have no signal to update from. That's why we have this huge sort of plateau here in the beginning. So here the agent's randomly exploring until it, by chance, finds the reward. Then it starts doing some backward induction towards the first state. So here the information is being propagated from the reward signal to all the states. So the agent observes, by chance, a reward at the green flag, and it's propagating this information towards the first state. And why am I saying propagating the information? Is because we are only updating the Q function in the current state, right? So it has to reach the state of the reward. Then for the state before, it's going to update, and then keep going like this until all the states have been, the Q function for all the states has been updated. So you see that even in this very simple case, exploration is tricky, right? So you need to collect data to understand how the world works. And even if the environment is just a simple grid world like this, so what it is taking? It's taking like a million steps to start converging, basically, right? So it's very inefficient. There are much more efficient algorithms for this kind of problem. And as Michal was mentioning in the lecture before, there is this sort of intrinsic motivation things. So one thing that you can try to do is to add some sort of artificial reward, some intrinsic reward, not a reward coming only from the environment. So for example, you can try to encourage the agent to incrementally visit more and more states. So you can, for example, add to the rewards a term that says, that gives a reward to the agent if it reaches a new state every time. So yeah, just to give some extra motivation for the exploration part.
We have a small question from the audience. It's relating to the previous step. So could you
of course.
please show the computation for TQ once again?
Of course, I'm just gonna show it here. I was preparing another notebook only with the solutions, but I'm gonna show it here. Yeah, so it's here. Yeah, thanks for the anonymous person who posted your reply. All right, so I'll let you digest it a little bit so you can keep exploring the notebooks. I'm going to post the solutions for both parts here. And in a few minutes, I'll move to the next notebook with you.
Like the formula is correct, but like is your previous correct? Like the PQ is, what do you have to do? No, forget it. It's okay.
I'm just asking whether we run this training on GPU or CPU. Did we set it somewhere? Because I get this notification from Colab that I'm not utilizing GPU.
For part 1 and 2, you don't need the GPU, no issue. For part 3, it still runs without the GPU, but it can be faster if you use one. So for this part, it's okay.
Let's get back for a second. Yeah, it's that. do some replacements with kind of like art. But yeah. Idea.
So is this part clear for everyone, part one? Everything we're going to do from now on really looks like this. So many things we're going to implement in parts 2 and 3 look like these two equations, but a little bit more complicated, but in the end it's the same thing. So I'm going slowly in this warm-up, so let me know if there's any blocking point here. It's important for moving on, so don't hesitate to raise your hand. So there's a question regarding a typo in part 2, so I'm going to check it. Yes, there's a typo. I'm going to show it here. Okay, perfect. Perfect start to go through part 2. Now let's start to make things more interesting. So we spent 1 hour with the basics. Because the basics are important to move on, I'm going to start to accelerate a little bit. So my goal now is to have, in 30 minutes, that we go until the end. So part 2 and 3, I'm going to give you I'm going to go through the notebook and the solution with you. And in the end, we have 30 minutes for you to try to reproduce the solution and ask questions if you have any. So let's get to it. So first of all, there was the question about the typo. So nice to see that people got here. So yeah, so it's A prime actually in this line here. So I'm going to fix it. If I find it, in itemize, so yeah, it's A prime here. Thanks for spotting the typo. Yeah. So it's A prime. We are maximizing over actions the estimate of the Q function. Okay, so as I told you, if I look again at part 1, let's take a look at the BEM operator again. Sorry for scrolling that much. Okay, so as I told you, the first problem here is, not the first, but one of the problems here is the fact that if the state space is large and we don't know R and P, this gets complicated, right? So one thing that we can do to handle it is to approximate the Q function as a linear function with respect to a set of features. Let me try to highlight it here. Yeah. It's a very poor highlighting, but I think I can point at it, maybe. Yeah, good. So we can approximate the Q function as a linear function with respect to some features. So we define a feature map for the states, and we try to learn or estimate the parameters theta A to approximate the Q function. So we have a vector theta A that, so that if you take the inner product of the state features, it gives an approximation of the Q function. And our goal here is to estimate these parameters theta A. And for that, you can iteratively solve many linear regression problems. So as you saw in value iteration, at each iteration, we are applying the BEM operator to sampling. And then we take the sampling, we apply the BEM operator again, and we continue. Now, instead of applying the BEM operator several times, we are solving several linear regression problems at a time. So instead of applying an operator, we are solving a linear regression. So that's the thing here. So QK plus 1 in the case of value iteration was a BEM operator applied to QK, so here. And now QK plus 1 is obtained by finding the function that minimizes this thing. So there's a regularizer, so you can think of the L2 loss if f is linear. And you are trying to match these targets here, which look like the BEM operator. So as I said, you're going to be seeing several times this reward plus gamma max here. So it appears every time, including in this notebook. And here we are using handcrafted features. And by that, I mean that we are defining ourselves the features here, the features phi used for function approximation. So let me show you how in this tutorial we are defining this function. So the environment again is the same. It's a grid world, but it's larger. It's a larger state space. And to give you some intuition, so we have about, I think, 200, 250 states. So it's still extremely small, but it's larger than the one before. And the thing is, we can use the fact that in similar states, so we have two xy positions in this environment. So the Q function should be similar for points that are close to each other. So the Q function here, so for example, in a state here, I don't know if, yeah, it should be similar to the Q function in a state right next to it, right? Okay, I think I lost the battery from this, no problem. Anyway, the thing is, if two states are close to each other with respect to the Euclidean distance, for example, their value function should be similar. So we can try to construct some features that encode this similarity. So if I take the features for one state, S, the features for one state as prime, they should be close to each other if the states are close to each other. So it should represent this notion of similarity. And here, it's a very simple thing that I'm doing. So I defined for you a feature map. So a feature map is this class that is taking an observation in a state and returning a vector with the feature representation for each action. So if we look at this, so we can create an environment, create a feature map, and to map the state 1 for, so it's the discrete environment, so the states go from 0 to the number of states, so it's an integer representation. So we map this integer representation to a vector in d dimensions, which is this feature example here. And if you want to, if you have a theta, so our value function will now be described by a parameter theta. And here is the dimension of the feature map. And we have a feature for each action, so that you can have a different value for each action. So there's one parameter, one vector, parameterizing the Q function per action. So in practice, if we want to compute an approximation of the Q function for the state 1 and a given action, and for any action, we can compute this matrix product here. So the feature map will have a shape, let me see here, number of actions by feature dimensions, and we multiply by feature dimensions number of actions. No, sorry. So this is just d dimensions, and this is d by number of actions. So we get number of actions features. That's it here. So here's the feature representation, and here it's the, let me check what I'm printing. Yeah, printing the shape of theta here. So theta is the number of, is the parameter, so you have 4 actions, up, down, left, and right. We have 15 dimensions of the features. So yeah, so instead of having one, so if you compare to the tabular case, we have a matrix number of states by number of actions describing the Q function. And here we have a matrix number of feature dimensions, so 15, which is smaller than the states, by number of actions. So we are reducing, we are compressing somehow the Q function into these parameters. And here, the 4 zeros is the value function for each action. So since theta is 0, everything is 0. Well, basically, so what we have here, so summing up, we have features for each state. So we can map from integers to a real vector. And with this real vector, we have a theta that we have to learn to approximate the Q function. And by multiplying those, we get the approximate Q function. All right. So what is learnable here is theta, and what's fixed is the features. So we handcrafted features, as I said. So let me check if I have the implementation here already. No, not yet. So if you run this notebook from scratch, you have all zeros here. And I think I'm going to go through the solutions directly. So I'll not spend much time in this part, because as I said, it's just to give you an intuition of what's going on. Okay. And while I explain, so I'm going to show you the solution. And then show you what happens when we change the features a little bit. And the message that I want to give to you here is that when we have good features, we can accelerate learning and have a more compact representation of the Q function. But at the same time, it's very easy to mess things up. So as long as our features are bad, you see that the behavior of the agent will be very different from what we would expect with good features. So in this part, we had 2 parts, 2 lines of code to implement, basically. So you need to compute the targets for your, so somehow the labels of your linear regression, which, again, is just reward plus gamma maximum over next state. And the difference here is that instead of, so let me put a comment here. I don't know if it's readable. Sorry, I'm going to increase again the size of the text. So the key point is here. So assuming you're getting more and more familiar with this kind of equation. So the main point here is that we are approximating QSA by this thing here. So sorry, yeah. So here we have a matrix, we have a function of SNA, sorry, S prime here because the next state. Basically, that's it. I'm going to put A prime, so it's coherent with the equation. Yeah. So here, just plug in the linear approximation of the Q function. So if you compare to what we had in qlearning, you had reward plus gamma Q next state maximum. Here we have reward plus gamma, this inner product maximum, right? So I'm going to put it in our solutions notebook, so you can reproduce if you want. So yi. Oops. I think it's here, yeah. Then the second part is solving a linear regression. So here the design matrix is implemented for you, so you can check the details of the code, but it's basically a linear regression. So it looks like a linear regression, but every time you need to recompute the labels, basically. Because every iteration you're updating your Q function, so in every iteration you have new labels, so new targets to learn from. And here I'm running once per action, so it's easier. All right, so by now the notebook should be running. So, and then at the end, what you see is the policy learned by the algorithm. So it learns, again, to reach the green flag. And below, I'm showing you an approximation of the value function. And you're going to see why I want to show this. Something very important here are the walls, right? So I told you that we built these features based on the Euclidean distance between states, right? So if you have the state 6, 6, it's close to 6, 5, right? It makes sense. But the Euclidean distance does not take into account that you cannot cross a wall. So if you're not careful with your features, your algorithm can think that it's possible to cross a wall. So if it generalizes too much, its behavior is going to be very bad. So here the solution is working when I put, so we have 200 states, remember that, about 250, something like that. And the feature dimension is 100. So you're not compressing too much here. So let's see what happens if I put 10. Oh, so it's running. So while it runs, I can show you again. So we have very similar to value iteration. You have a number of iterations, but here we have a linear regression instead of the application of the Bellman operator. Now let's see what happened when we decrease the feature dimension. So the agent got stuck here. It's not moving anymore towards the green flag. And let's look at the approximation of our Q function. So it's horrible. Makes no sense because the rewards are here on the top the top right. And in the value function should be high, where roughly around the reward, because that's where we want to go. So let me increase again to 50, let's say, or yeah, 50. Let's see what happens. Sorry?
What is more than 100?
If the dimension is more than 100?
Yes, we saw that the
Yeah.
100 is the best dimension. But what happened if we have more than 100?
So if you have more than 100, you're just getting closer to the number of states. So you can think of the extreme case where your feature dimension is equal to the number of states. So here it's possible because the states are discrete, so it's not always the case. But if you put the feature dimension equal to the number of states, it's basically equivalent to having a table to represent your Q function. So you have number of states by actions features, which is basically the same thing that you need to store the true Q function. It's number of states by actions. So there is no information loss when you are using features. So it's basically almost equivalent to the, it gets very similar to the value iteration. And the difference would be, there will be two differences. So there's this regularization lambda, so for the linear regression, so we could put it to 0 and get rid of this difference. Another difference is the sampling. So the algorithm can also be sensitive to how you sampled the data set of states and actions. So here, what I'm showing you, I think it's a uniform sampling. So we sample n points. Every time you sample a random state, you get the transition from there. But your results can be very sensitive to the distribution of your sample data. So if you're following a random strategy from the initial states, so let me show you here. So if you're following a random policy starting from here, there's a very low chance that you get to the reward. And assuming that you get there, there's going to be many more points here near the initial state than in the other state. So your approximation can be bad due to this effect of sampling. So there are other sources of error compared to the case. So even if your feature can represent exactly your Q function, there is this sampling issue.
Thank you so much.
So yes, so let's see what happens when so when I increase to 50, did it work? Yes, it works. Yeah. But if I put 20, well, I think just to show you that with certain tuning, the agent can hit a wall and stay stuck there, basically. So if you generalize this too much, so if the value function if the value function is assumed to be continuous across a wall, the agent can get stuck hitting the wall, for example. Let's see if it's the case here. Yeah. Well, it got stuck here, but well. Yeah, I'll let you play with the feature dimension, but it's basically that. So you can also increase the sigma. Let me put 50 and increase the sigma to 100 to generalize. But anyway, I think you saw the failure cases. So if your features are not good, your agent will get stuck because it's generalized badly or the convergence was bad. So now this is preparing the ground for deep qlearning, right? So here, as you might expect, so we were solving a linear regression in every step. So what's going to change when you go to deep neural networks or neural networks? Not so deep sometimes. What's going to change is that we are not going to take the argmin every time, so we're not going to solve the full optimization problem every time. We're going to take a gradient step, and there are some tricks to stabilize the learning procedure. So it's very tricky because, as you saw, the targets of your linear regression, they are changing every time. So it's like you're trying to learn something, but your targets are moving. So you're bootstrapping what you learned from the past. So if you're not careful, this can lead to a very unstable behavior. So you have to be careful about your function approximation, about how you sample data, about learning rate, and many things. So many things start to get complicated when you start using neural networks here. So just to, yeah, sure. Finally got to show you a case where it gets stuck in the wall. So if you look at the agents getting stuck here, and probably it's because the value function generalized too much. So if you look at the value function, it looks continuous across the wall, but it shouldn't be, right? So the value here should be much smaller, should be almost as high as across the wall. So these very simple examples, you might think, okay, we don't care about grid wars, they are very annoying, let's go to Atari. But even in these very simple examples, you can get interesting intuition. So you can see how a bad feature can lead to this kind of problem. You can see how generalization can help you, so you can really have a more compact representation of your Q function if you can generalize across similar states, and you can see how things break. Now let's move to deep qlearning. So we still have 40 minutes, which is good. So as I said, I'm going to go through the solution of deep qlearning with you, so you have time to copy the solutions yourself and ask questions in the end. Okay, now we have it here. Let's go to deep qlearning. Okay, I don't have my kernel anymore. So I'm going to execute everything again. But OK, so let me start by the equation and comparing to the previous case. So before, you had a very similar thing, but instead of these parameters here, and instead of having this loss, you had a linear regression. And now, as I said, we are taking gradient steps to minimize this loss. And there's, as I said, there was one trick that's very important to stabilize your learning problem. So assume that you have only one neural network for estimating your Q function, right? What's going to happen? So if you try to minimize this loss, you can see that the target depends. So ignore theta minus for now. Assume that theta minus is equal to theta. Sorry, I'm going to increase the size again. Yeah, let me see if I have it. No, you don't. Anyway, assume that you don't have this target network. Assume we only have one single neural network approximating the Q function. So we are trying to minimize this loss. And the targets, so the labels that you are trying to match, they depend on theta. So it can be very unstable, right? It's like when you imagine, for example, if you take a classification problem, and in every gradient step that you take, the labels have changed. You cannot really reasonably expect to convert to something. Maybe it will work on some cases, but it will be very unstable and really hard to make it work on real problems. So the trick here is that we keep two neural networks. We keep a neural network with the same architecture, but we keep two sets of weights. We have what we call the online network, which is the one that we use to interact with the environment. So every time we need to sample an action in the environment. In the Epsilon grid strategy that I mentioned in qlearning, so you take a random action with some probability, and you take the best action according to Q theta, with 1 minus epsilon probability. So that's why we call it online network, because it's used to be for the online interaction with the environment. So, and then we also keep a target network. It's a network that we're going to use to compute the target, so the Y here, or targets or labels for the regression problem. And how it's going to stabilize the problem. So the target network is not updated as often as the online network. So you only update the target network after the online network parameters had time to converge. So you're going to see you minimize the loss, you change the target, you minimize the loss again, you change the target. So it's a so if you compare to value iteration or fit or linear function approximation that I just showed, it's the same idea, right? You are applying the Priamo operator, then you change the target and you apply it again. So it's very similar. So it's a sequence of supervised learning problems, and every time that you move to the next step, to the next iteration, to the next part of the sequence, you change the target that you're moving, right? And your goal is to converge to the optimal Q function. So here, all the code is set up for you. It's more complicated than should be, the code here, but I wanted to give you something that is general enough so that you can try complex ideas. So if you remember Mihal's lectures, for example, there were losses based on trajectories. So we not only, so if you look at the loss here, sorry, I'm going back again to it. If you look at the loss here, it depends on a batch of states, actions, rewards, and next states. So for qlearning, only sampling that would be enough. But sometimes you want some trajectories. You don't want just states sampled randomly from your past. You might need to sample trajectories to compute some more interesting losses. So I wanted to give you a code that you can use as a starting point for ZQN, for GPU networks, but that you can also go from it to more complex settings. So what this code is doing, so if you followed the qlearning part, it's very similar for the interaction with the environment. So all the things are happening in the fit method. We have a loop on time steps. Every time we take an action. So we have a method called actor step, which is implementing the Epsilon greedy strategy. So with probability epsilon taking a random action, and with probability 1 minus epsilon taking the greedy action. And notice that this epsilon greedy strategy is only for when you're interacting with the environment. If you're going to apply your policy, like in an evaluation setting, not in a learning setting, you need this policy to not be random. So you put evaluation equals true if you want the policy to be deterministic. So if you're in evaluation mode, you just want to try your policy in the environment, you can put evaluation equals true. But basically, what you have to implement here is the loss. So I wrote everything except for one line in the loss. Let me see if it's implemented here. Yeah, not implemented here. So all you have to do is to implement the loss here. And the sampling is done here. So the loss function is taking the parameters of all networks as input. So by all networks, I mean the online network and the target network that I told you about. And we have batches here. But these batches, they are not only batch size by dimension, as you might be used to. So it's batch size, B, T for something that I call chunk size here, and some other dimension eventually. So the dimension, the dimension of the state space. So here we are trying initially to balance a pole. So the pole is going to be, so you have the position and velocities of the joint. So I think you have a 4-dimensional state space, if I remember correctly. So it would be 4 or 6. And what is T here? So we don't not only have a batch of states or observations, we have the trajectory that was observed following this state. So we have a trajectory here. Of course, I'm flattening it out, so you get something that it's roughly the batch size as input and the rest here. So that's what you're going to need for qlearning. But if you want to implement multi-step returns, qlambda, don't worry if you haven't never heard of it. Those are some improvements that you can test on deep Q networks, on deep qlearning. You might need the time dimension, but not for deep qlearning. So here, what are we observing? So I'm going to code this with you. So here there are two things. So let's forget the Q select for now. It's used for double qlearning if you're familiar with it, but otherwise don't bother. So here we are computing roughly Q of ST80, let's say. Here we are computing Q of ST, sorry, it's for all actions. So you're computing Q for the current state. Here we're computing Q ST prime, so for the next state. So either ST prime or ST plus 1, depending on the notation. Okay, so now let's implement our loss function for the QN. And if you remember correctly, let me show you again the previous solutions. It's going to look a lot like these things. Reward plus gamma, maximum over actions. So let's implement it here. And there is always a bug when I implement this the first time. A practical advice, always check the shapes of things when you're doing your loss, because there might be some implicit broadcasting that, anyway, check the shape. Okay, so what are going to be our targets for our neural network? Any idea? You all know that, I hope. It's going to be the reward. So here it's not called reward, it's called RT. Another thing that is different here, I'm storing the discounts at every time step. So the discount is gamma almost all the time, except when you reach a terminal state. So for example, assume that your rocket has landed or that your pole has fallen. So you reached a terminal state, so you don't have a next state. So when you don't have a next state, so let me show you some equation. Yeah, for example here, when you don't have a next state, so when a next state doesn't make sense, you can set gamma to 0, and that's what we're doing basically. So this here, yeah. So this array It just indicates, so it's gamma everywhere except where we reach the terminal state, where it's 0. So it's taken care of here. But basically, it works the same. So we can discount t, so it's gamma, times, so we have to compute q for the next state. So it's going to be this one. So we have all the q functions for the next state, and we maximize over actions. So n, so let me call it current q because it's the current value of the q network that we want to match the target. It's going to be what? So it's going to be qt. Well, so if you look at, if you pay attention to it, you see that the parameters here are different. So we have the parameters, so it's the same architecture, so the same apply function in JAX. So the same architecture, but the parameters are different. So for QST, we are using the parameters of the online network. And for the targets, we are using this one for the target network. So I'm going to call it online queue, so it makes sense with online and target network, online queue. So what we want here is to take for the actions that we selected. Yeah. So can anyone see a bug here? Probably an underscore. The underscore is, I think it's fine. Let me check for this one, it's fine. It's actually very subtle. You might think that you're taking the indices here. There's a broadcasting going on if you don't do this. So check the shapes. Shape. Now no broadcasting is going on. So basically the shape of this thing is going to be b times t, so roughly the equivalent batch size. So batch size times the number of time steps in a batch size, because we've fattened everything before. All right, so I think it should be okay, unless there's a typo. And the loss is going to be just JAX numpy. The square loss, mean square loss. You take the values of your online minus target. So it's the square, so we take the mean. Let's see, it's not working. Never works the first time. If it does. By the way, just I didn't mention before, let me open some parentheses here. I'm using, so the tips for the GQN implementation, not necessary, I went through it with you. I'm using this library that we developed in my lab when I was doing my PhD, so I will contribute a lot to this. Its goal is to help you develop reinforcement learning from scratch. So there might be something that you are seeing in the tutorial that come from this library. So the goal of this library is basically to give you tools that allow you to go from debugging to training multiple agents in parallel, and to easily integrate code and agents from other libraries for benchmarking, etc. Because in reinforcement learning, it's very difficult to debug, right? So as you saw in the first notebook, you have a huge plateau when you're doing qlearning in a tabular environment. So if for a long time you don't receive rewards, it can be a mess. So imagine that you're looking at your loss function, everything doesn't change. It's awful. So it's important to have a clear methodology for debugging. So grid words can be annoying, so these 2D environments can be very annoying and uninteresting. But as you saw in part 2, for example, not here, but maybe here, it allows to visualize precisely what's happening. So if you're implementing some algorithm from scratch, I strongly suggest that you try on grid words first, just to make sure it's running, that the loss is converging to what you want. Because once you move to Atari games, to robotics, it can be very, very hard to debug. So you're going to implement your algorithm. It's not going to work because, well, when does it work for the first time? And then you don't know if the problem is a bug in the code, if the environment is too hard, if the hyperparameters are not good. So it's important to make sure that first the code is running as expected in an easy environment, and visualization is very important for that. So now I think, let me go back to the tutorial. So here I'm using, from this RLberry library, something that is called agent manager. So it's basically taking your agent class, some hyperparameters, and running it in parallel. So I'm fitting 2 agents in parallel here. Let's see if it's working. So yeah, and you can follow a little. So there's going to be plots later. No, it's not a good notebook, so yeah. Let me see, I think I didn't run this cell. Yeah, oh, look, of course, forgot to remove this line. Okay, so let me interrupt the cell below. You see, you cannot see loss equals to exactly 0, never happens, maybe. No, don't restart. So I'm gonna run the cell again. Let's see if it works. So of course, so here it's commented some parts where you can fit just 1 agent. I like to have some idea of the variance of things. So 2 agents are not enough, but basically you can increase it if you want. Let's check the loss. Okay, so there's some loss. And then you can, so just to give you some idea, the episode rewards are the rewards that are collected during an interaction in the environment. So you're trying to balance a bar. Let me see if it's here, a poll. So you're trying to balance this poll, and the episode rewards is the amount of rewards that we got while the bar was balanced. So yeah, you get a reward of 1 or -1, I forgot, while the you get a reward of 1, sorry. Every time step that the poll is balanced, you get a reward of 1. When it falls down, you get a reward of 0. So if you try to maximize the sum of rewards, it's balancing the poll, basically. So let's see what's going on. So you see that the rewards in the episodes are not increasing too much, so there's probably something wrong, as usual. Let's try to debug. Yeah. Exactly. Thank you very much. And there's another thing here that is wrong. So, anyone see another bug here? Live debugging, super cool. Let's go. Remember that I said that the target network was only updated periodically? But yeah, the code elsewhere is updating it. So I think it's, if you look at the fit method, yeah, it's, let me see. It's been done somewhere. It's not the issue. The thing is, we are taking the gradient of everything here, right? So maybe we are taking the gradient also with respect to the target network, right? So how can I prevent gradients being taken with respect to the to these ones from Qt value for the value? There is something missing here, right? There is a stop gradient missing. Because you don't want to take gradients with respect to your targets. Let me run it again. So yeah, so there was a bug here, so it's good to maybe check, even in this case, to check out the loss function. Sorry, the loss. So there's a function here to plot everything. So yeah, so you see that the loss is whatever. Doesn't look nice, right? And the rewards also not increasing, so it's pretty bad. So let's try again with the bug fixed. Oh, how can I? Yeah, this. It's here. I'm going to train only one agent to go faster, because there's probably going to be another bug. And while it runs, I'm going to show you an interesting library for you. So you might be wondering why I have this weird naming of variables. Not so weird, actually, depends on what defined as weird. But you can look at this relax library by DeepMind. It gives you lots of nice loss functions already implemented for your algorithms. So, for example, if you go to relax source, so as I told you in the beginning, we are interested in approximation value function. So there is value learning, and you can see qlearning. So you have the qlearning loss here, you have double qlearning, you have variations of qlearning. So I took their naming convention. So if you want to explore this library with the code I provided, you can. So just a parenthesis while the code is running. Let's see. Yeah, now you see the episode rewards going up. So we got 128. Nice. So it's still running. So yeah, you can see the evaluation rewards. So while it runs, I'm going to start copying the solution to our solution notebook. Okay, where are still running? Okay, it's done. Nice, so let me decrease the zoom so we can actually look at the plots. Okay, so now it makes sense. So you might wonder, okay, this qloss function is horrible, but actually it's learning something. So you'll see that the rewards are increasing, of course, in a very noisy way. So qlearning is super unstable. So deep qlearning is super unstable, even if we did all we did. So there are many improvements that you can try on qlearning. So what people usually do, I think, in this case, is to do some kind of early stopping. So as long as you reach this high reward, you can stop, for example, your training loop, so that you get something that works. So why is it unstable? Just to give you some intuition about that. So when you are acting on the environment, remember that you are taking a maximum over actions. So for each state, we compute. So we take the state, we pass it through the neural network, and then we take the maximum output of the neural network, right? So you're taking a maximum of something that is being learned in a stochastic, complex way. So the maximum can change quite fast. So from one iteration to another, your policy can change very drastically. So there are ways, there are like some soft qlearning versions that allow you to do more conservative updates. So instead of drastically changing your policy from one gradient step to another, you can do that more slowly and make sure things are more stable. So basically, there are ways to make this more stable. And there are also policy gradient algorithms that are based on learning the policy directly. And oftentimes, they have explicit constraints on the difference between the updated policy and the previous policy that can make learning more stable. But anyway, so when I look at this kind of curve, so you can see that every peak here is because the target network is being updated. And so I'm also doing a hard update. So periodically, the weights are copied from one network to another. You can do some exponential averaging too, some moving average to update it. Basically, so there are things you can do. But I think these peaks are somehow a sign of life that you're getting something from the QN. So often when I start observing these peaks, your implementation is going in a good direction. It gets completely messed up later, but sometimes it's okay. Let's see the video now. So yeah, it's doing something, right? You can improve it. I believe in you. But well, so if you compare it to a random policy, it's already a little bit better. But of course, GQN is able to solve this environment. So if you want a very nice pole balancing, I suggest you do an early stopping, or that you start looking at some multi-step return. So in RLX, you have Q lambda. You may try Q lambda. Lambda, yeah, you have, let me see, Sarsa lambda. Yeah, you have a Q lambda function in RLX. So you have everything here. So let me zoom it. Sorry, probably not readable. So in RLX, so you have all these quantities already. You have Qt minus 1, AT minus 1, RT. So you can use this loss function from RLX if you want to do Q lambda. Yeah, basically that's it. So I'll let you still have 14 minutes. I'll let you play with it. And just give me 2 more minutes for me to present the challenge. So you can think, oh, the challenge is not super challenging. It's just a huge grid word, of course. But it's a preliminary step if you want to tackle things like Montezuma's Revenge on Atari. In Montezuma's Revenge, you're trying to move from one room to another. So if you cannot solve this, you cannot solve Montezuma's Revenge. So it's a very important debugging step, as I was saying. Start simple. So here you don't have many representation learning issues. Here representation learning is easy. Your main issue is exploration, so how to collect data to explore different rooms. So basically that was the challenge that I gave for you. So if you want to implement some exploration strategy, so here you can go crazy, you can play a lot. So you can start simple with some intrinsic motivation, random network distillation. I'm going to put some references in the GitHub later. So you can start simple with some baseline intrinsic motivation techniques. You can go crazy. You can put reinforcements. You can put representation learning on top of it. You can put bio explore, as Mihal was presenting. So there are many things you can do with the simple notebook. And here, when you make it work for cart pole, you can go to the beginning and also select lunar lander if you want to see the rocket landing. So yes, so I'll display the solution here. Let me know if you have any questions. So for the last 12 minutes, I'll let you try to reproduce what I did, play a little bit with it, maybe balance the pole, and answer questions. And by the way, these things can be quite annoying, right? So you saw that I had to include these indices here. So one thing that's cool about JAX, you can have the loss function assuming that you don't have the bad dimension, then you vmap over it. So the loss functions in RLX, you need to vmap them. I'll post a solution with that later, but so here it's easy because you only have 2 dimensions, but if you start having batch trajectory size dimension, vmap can help you avoid some bugs. And just one last thing for you who like self-supervised learning, representation learning, this kind of thing. So if you look at this qlearning loss, there's some bootstrapping involved, right? So you're bootstrapping a Q function to compute the loss. You see that the loss is somehow not converging to 0. So if you want to think about it, you can try to think about why BYOL that Michal was presenting before, so it's this self-supervised learning method. You can think of why it doesn't collapse, why doesn't the representation collapse. You can try to make a connection between the bootstrapping happening there and the qlearning loss that you observe here. Might be interesting too.
There is actually a question in Slido. If you see it, you can
Yes.
probably read it and answer.
Thank you. It's a good question. So when the implementation is not available, well, when you don't, it's always better to start from, if you're comparing your agent, so you're doing your research, you're developing your agent and you want to compare it to a previous paper or another algorithm, I think usually the good practice is to take the code as reported by the authors, so you can compare exactly to what the authors reported. And oftentimes in reinforcement learning research, what people do is when they are trying to build on some existing algorithm, they take the author's code or some standard baseline implementation and they build on top of it. So because implementing from scratch can be quite difficult. So for research, I always like to implement from scratch at least once, just to get an idea of how difficult the tricks are. Then I move to the author's implementation or somebody else's code to make sure everything is working. So if I try to sum it up, I would say that try to implement things from scratch. It's oftentimes not going to work as you expected, but it gives you can learn a lot by implementing from scratch and debugging. And then you can move towards, so there are several cool libraries that I'm going to cite in the GitHub. So there's stable baselines, there are several DeepMind libraries with standard implementations that you can use. And if it's not implemented in these somehow standard libraries, try to use author's code as a starting point. And if not, at least try to compare to someone else's implementation. It's a good practice. But it's tricky. Once I was implementing one paper, I went to the author's GitHub. I was trying to make it work in my own implementation. And in the end, I saw that the hyperparameters in the paper were different from the hyperparameters on GitHub, and that changed everything. So even when you have the code from the authors, it can get complicated. So yeah, it's hard to code in reinforcement learning, but it's doable. And by the way, just to make some sort of publicity again for this library. So the goal of this library is to isolate all the training code inside the fit method. So if you look at the deep qlearning tutorial, let me show you here. So yeah, there's a fit method where you can put everything. So what we did is that, so sometimes you can really copy-paste an entire implementation from another paper. So you have a common framework to compare your own implementation to other people's implementation. So that was also one of the goals of the library, to make it very flexible to integrate other people's code for research. So you can have your own implementation and every time compare it to another baseline reference implementation. All right, so we have 1 minute 20 left. So if you have any question, let me know. Okay, so I'll just conclude in this last 55 seconds. So here what I try to show in this tutorial is how to go from a very simple grid word towards something that can lead to a more complex implementation. So here, as you see, these things are very similar in the inside. You see, I always have this R plus gamma next state, somehow approximating the Bellman operator. So you're going to see this very often in reinforcement learning. So here, and when you go towards more complex things like deep qlearning, I provided you a code that is, as I said, a little bit more complex than it would be for an usual DQN implementation, but you can build on top of it towards more complex things. You can put representation learning losses, exploration bonuses, losses, intrinsic motivation. So don't hesitate. So if you're interested to keep exploring this direction, so try to improve the stability of the QN, try to improve exploration, try to include representation learning, and you can send me an email or contact me if you want to discuss more about it. And that's it. So thank you very much.